All right, my name is Kerry Wood. I'm actually a contractor at Army Research Lab. Rich wasn't able to make it, so I'm here today. As it works out, I wrote most of the paper, so that's not a problem. If you have any questions and I can't answer them, I'll blame them on Rich, but I'm totally punting. We are going to take a little bit of a different look, and right from the get-go, I'm going to put a caveat in that I am not a formal language guy. I am new to all this. I put computational complexity on my resume and started down the rabbit hole. That was about a year ago. So if I say something stupid, it's because I'm probably stupid. So please clear it up for me. Basically, the beginning of this was a natural, literature review, right? You start out, especially when you don't know what you're talking about, looking at all this stuff. And it's a rich field that's been looked at for the better part of, I'd say, 40 years. Deciphering some of it can be interesting. There's edge cases, there's specifics, and because of that, this is just going to be a teaser, especially this talk. If you're interested in this at all, I definitely recommend you look at my paper, which cites a lot of other papers. So mine is kind of the beginning of, hey, take a look, go look at these other references. You're never going to find one that's comprehensive. Even the closest ones are going to be 50, 60 pages. We came into this kind of knowing that inferring grammars is difficult. So if we go and stand before Army leadership, we say, this is something that may work, and if it does, it would be great, but we're pretty sure it's not going to. We also think it's probably harder to bake all this into every piece of code that's ever going to be written for the rest of time. So it's a kind of a natural, converse way of looking at the problem, and we hope we've seen a little bit of progress, but the results are minimal at best at this point. Just a quick overview. We're going to do a brief introduction of grammars and LangSec. We'll skip through that pretty quickly. Mostly that's to kind of scope what we think LangSec is, especially from our perspective. Models of learning, definitions are extraordinarily important when you start looking at these references because a slight change in one to another can be a completely different computational complexity class. Models of teaching, how is data presented? Is it available? That's also important, not only in, like I said, reading these results, but in applying them to real world data and systems. Part of this also in this literature review is to say, can we take problems that we're already looking at, intrusion detection, anomaly detection, can we look at them in the scope of formal language theory? So we can get into that a little bit if we're interested, but there were more goals than what I'm going to talk about here. We'll talk about two specific constructs, pattern languages and elementary formal systems. I say they're our favorites. They're my favorites. I don't know if they're our favorites, but EFSs, I think, are some of the more interesting ones, although they're kind of hard to work with. Some initial work, and then hope springs eternal. I'm going to tell you about all the wonderful things I'm going to do, hopefully, someday. This is the slide we'll probably fly through, just the background. We all know the complexity goes up as you crawl up the Chomsky hierarchy. Depending on who you talk to, you never want to be out of regular. You certainly don't want to be out of context free. Once you get here, you're in real trouble. The question is, can you even infer those classes? And the answer is almost always no, but we'll talk a little bit more about that. The grammatical inference problem is pretty simple. You're given a bunch of strings, and again, we'll talk about how they're presented and how many of them you get to see. You have to identify this generating structure in whatever your favorite formalism is. In essence, you're kind of decompiling the grammar. It just is much harder because these tend to be asymptotic arguments. So you can have grammars that are infinite. How do you infer an infinite grammar, right? If it's simple, you might be able to pull it off, but in the grand scheme of things, you probably can't. In a teaching model, they actually do infinite presentations. So you have to see every string from the infinite grammar before you can infer the grammar. That's going to be a problem in the real world. So obviously, we look at those bounds, but they're not all that useful. This is kind of our view of why LangSec is important, and I think everybody in the room tends to agree. I'm glad, because I've heard some comments this morning. I've got a little sheet of paper with all the things that I've heard that agree with me. I didn't write down any of the ones that didn't. You have all of the possible messages in the universe. You really want to accept the little green bubble. What you're probably accepting is somewhere in the middle, and that circle can be defined in lots of different ways, right? So it depends on what the programmer meant, what the grammar meant, what you really meant, what the security guy meant. And what we'd like to do is kind of have an idea of which of those and the scope of the grammars that actually build those strings. The trouble begins when we need to define the recognizer, but we actually define one for the top one. And that's what we do most of the time, right? So we define this one, we mean the little green ball, and exploits, exploits, exploits. We'd love to use only simple grammars with provable properties. I heard the keynote this morning, and the question I wanted to ask that thankfully Michael asked for me was, it seems like you want to teach people how to do this, but how do you convince them to do it? Because at the end of the day, they're moving bits from one end to the other, or they're taking their bits and doing something with it. And I don't know the answer to that. I also don't know if it's really possible because defense is nowhere near as sexy as offense. Never will be. Playing defense is like playing offensive line for a good football team, right? Nobody knows your name unless you've screwed up. So it's a tough job. So I think the tools have to be there, and I think there has to be an intuitive way to tell programmers and consumers of this kind of information what they're actually looking at. And that was part of this research as well. I think we know all this. I will skip through most of it. This is where it starts to get interesting. When you look at the literature, almost all of the papers are going to talk about learning from positive examples. So in a sense, you're presenting examples from the grammar to a learner repeatedly, usually until you've exhausted the entire grammar. You've given them every example that could possibly be constructed. Again, it's not all that interesting, but even under those constraints, you still can't learn a lot of grammars. That's pretty shocking when you think about it. So even if you're presented with all the examples, you're never going to learn the grammar. There's the possibility of positive and negative examples. This is a complete presentation, much more powerful. Many more grammars are learnable under these constraints. Learning with an oracle, learning with a teacher, and then compressed simple examples. There's this corpus of research, and I don't want to get into the details, like I said, because I will bore you all to death on the second talk in the morning. But every one of these models has different results. And I think that every one of these models maps to a small segment of what we actually do every day. So there's a slide actually at the end, but just keep them in mind as we go on. So the models of learning, again, the model is pretty simple. A learner, in this case, we call that script A, takes some data D and outputs a possible generating grammar G. Now, whether you can verify that grammar, that's also up for debate sometimes. And you have these specific types, and you'll hear these terms thrown around, learning in the limit, which is gold-style learning, kind of kicked off this field of research. The learner is presented sequentially from the entire grammar, and then at each iteration it guesses. So eventually it converges on one, right, and says, I'm never going to change my guess. I think I know the grammar. But even asking that learner to stop and say, yes, I'm never going to change, is something that changes the complexity class. Again, I won't get into the specifics, but the problem itself gets very intractable very quickly, and the reason to talk about that and keep saying it over and over is because we end up getting simpler and simpler in what we're actually trying to learn on purpose, and I think it actually maps pretty well to what we're trying to do in the real world. Down here, probably approximately correct. Given access to examples, you basically output a guess with a certain accuracy bound, and you can tweak these bounds to decide how much data you need and how sure you want to be about your answer. This tends to be where most people want to play these days, and I think it's probably the most interesting. Unfortunately, the results in terms of learning don't get appreciably better. I drew this little diagram for somebody, and I wanted to include it here because after you hear all that and your brain's kind of spinning and it sounds horrible, really, at the end of the day, the only thing that happens is examples come in, the learner looks at them and outputs a hypothesis. Eventually, at this dotted line, they stop guessing. They say, I'm done, I've fixed myself on a candidate grammar, and I'm going to stay there. So don't get too, let's not go too far down the rabbit hole. And I'm sorry about the subscripts for some of the examples on the left-hand side. Those can go off to infinity. One of the few constructs that actually is shown to be learnable by Dana Angwin was the pattern languages. For those of you who have never heard of them, and I don't expect anybody to have heard of them, they're regular expressions. Heavily restricted regular expressions is the best way to think about them. You have some constants that turn into strings. We have variables, and then patterns are comprised of stuffing those variables into strings. You map out a substitution, and I'm just showing some of the notation pulled directly from the paper. Again, it's kind of a teaser. This is pretty standard notation. The key here is that empty substitutions are not allowed. Remember I said at the beginning, you change one little thing and all of a sudden the results fall apart? If you include empty substitutions, it gets even harder. Then the patterns that are actually generating the language change completely, and you end up with a completely different learnability result. So regular patterns are probably the ones that we're most interested in because they're the most likely to be learnable, and that's where a variable appears just once. So you can have x1, x2, x3, but not x1, x1, very simply. They're somewhat natural. They show that they're learnable. This Lang and Wehagen algorithm is 20 lines of Python. If you want to write it and learn yourself a pattern language, go for it. In general, the bad news is that they're NP complete even to determine membership. So if I give you a pattern and I give you a string, it's actually NP complete. In most examples, let's be honest, the string isn't that long, so it doesn't matter. It's still fairly tractable. They do not map to Chomsky. They're actually orthogonal. So you can't look at a pattern and say, beyond the regular patterns, which are pretty heavily restricted, that they fall into one of the Chomsky hierarchy a class in a hierarchy, excuse me, relationships are very hard to determine as well. So not closed under union, lots of academic subclasses, and pack learnability is hard. They sound awesome, right? The only one we've gotten to really work. So not exactly all that encouraging, but like I said, they're very intuitive, and when you throw lots of data at them, they make sense relatively quickly. The reason to even mention stuff like not closed under union is because really when you start implementing these things and you try to learn grammars in the real world, you end up kind of reducing your state space and reducing your space and reducing your space until you get a problem small enough that you think you can actually do something with it. So we'll talk about unions in a little bit, but that's where this ends up going. My favorite, again, are these elementary formal systems that came out of Smullyan's paper back in the 50s, talking about recursive theory that turned into a universal formalism for grammar inference and writing down and accepting grammars. And basically, do we have any people who write Prolog? One. I knew if I asked it in this room, I'd get a yes. I've asked it 1,000 times, and I don't think anybody's ever really said yes.
That's context sensitive on the top, and that's context free on the bottom.
Right. It maps, if you know it, it maps beautifully. It makes a lot of sense. The grammar is, and I've heard this over and over, the grammar is the language, right? It's easy to write them. Unfortunately, everyone, no offense intended, hates Prolog. So it turns out that trying to sell this to people is a bit much. But the good news is that even the learning algorithms, while they're terrible in terms of computational bounds, are fairly natural, because to determine whether or not you have a member of these grammars, you're actually kind of walking the tree. You're doing assertions and plugging in substitutions. So one of my favorites, and this is why, all you have to do is put very natural restrictions on the elementary formal system, and they map very nicely to the Chomsky class. So variable bounded are recursively enumerable, everything you can ever write. Length bounded, regular, and the regular are actually context free. So our regular EFS maps to context free, and then right left linear maps to regular. Like I said, there's a reason that it took me forever to do the lit search, because that alone, I have about 3 pages in my notebook with a big box written around it that says regular is not regular for EFS, because when you start doing it over and over, you get pretty confused. But again, these are fairly natural constraints on building those elementary formal systems. If you consider elementary formal systems natural in any way, shape, or form, then they map pretty well to the Chomsky hierarchy. And what's even nicer about that is that pattern languages in and of themselves are actually a single class of EFS. So it's just an assertion. So it's effectively an EFS, but it doesn't really fall into the overall hierarchy, or I'm sorry, the framework. When you put a few restrictions on an elementary formal system, and this is called a hereditary clause, and the notation's kind of onerous, but really all it says is that any substring contained in the right-hand side, which is kind of the asserting part, it's an if-then clause. On the right-hand side, you're essentially saying if you can prove those individual components, then the left-hand side is true. On the right-hand side, any substring there has to be a substring of the left. Again, very natural constraint. Then you get some pretty good learnability results. And I pulled this chart right out of the paper, and really, and I didn't actually label the columns here because it's easier to explain them. But all we're saying here is that infinite is not learnable and finite is. That's really all that those columns mean, which you'd expect, right? I mean, if you're given enough data out of a finite class or out of a finite grammar, you should be able to pull it out using those components. This notation basically indicates that you have to bound the number of clauses. Again, it's that asymptotic argument, and then variable occurrences in the head of each clause. So the number of variables matters as well. That's the real constraint as far as I'm concerned. Obviously, this one's pretty notional, right? I mean, if you have infinite clauses, you would expect not to learn that before the universe cools. So if we look at a bunch of different problems this way, and this is the slide when we're presenting to management and they say, okay, why? Why do we care? Because they don't understand any of this stuff. And you ask them the difference between a parser and executing code and their eyes spin. I think a lot of these problems that we look at are actually best described as some of those differences in grammar. So supervised learning problems, we have these anomaly detection problems, fuzzing, which we'll talk a little bit about later, and of course unsupervised clustering. Can we look at it through a framework of grammar inference, right? Because some of these problems are so hard that you can't ever hope to do them. So are these problems actually manifestations of that, where we could say, just stop looking for that science of security answer that we keep throwing money at, that you're actually trying to solve a problem that's unsolvable. What we did find is obviously that simple is better. Simple is inferable. So our hypothesis is that most data in the wild comes from simple grammars. And this is because our ARL especially, we have a mission as a I shouldn't say we, I'm a contractor there, but ARL has a mission to do computer network defense. So they are actually paid by other companies and other pieces of the government to watch networks, which means staring at snort logs, for lack of a better description. But we get access to lots of data. And when you look at data in real world systems, especially on the military side, a lot of it is fairly simple. There's lots of stuff out there that has complexity, but when you look at what you're really trying to do, you can actually peel out pieces that make sense and are those little examples I talked about where you can actually learn something. So even though a protocol, and this is what Sergey said this morning, he says if you have protocols that are everything to everyone, that is bad. That is true, but they all start that way, right? So the Army loves to install these software systems that they buy or they go get that are open source, that are all-encompassing and do everything from make coffee to polish your car, you know? But really, they use this tiny little piece. And if we get that tiny little piece out, that's great. So that's what we're trying to do initially, is sometimes, you know, even just classifying a message is a good place to start. And are most messages as complex as the overall grammar? Empirically, I don't have the data to say for sure, but no. I mean, really, in most cases, they're very simple subsets of the overall huge grammar. And then what we're trying to do, and this we'll talk a little bit more about in future work as well, is use the program itself as a guide. So the program is, in a sense, a recognizer that can help you teach the grammar, or learn the grammar, rather. It acts as an oracle. So we have all this data, and we have what we think are pretty good sensors for some of this stuff to keep the bad guys out. So we have good examples of what we really want to accept. Can we segment these big problems into smaller problems and then start limiting what we're actually accepting? The very simple, like I said, pattern language example, you start here because if this is totally non-intuitive and it doesn't work, stop and go work on something else before they take away your research money. We have huge logs of post and get requests from Army systems, and they're notionally anonymized. All I did was just map characters to preserve the structure of the URL and get it through my Form 1 public release process. So you can kind of see the structure here. We break down by endpoint. Obviously, most of the good requests we get are extraordinarily structured, and we would expect that. So when you plop, the nice part is when you plop in something that someone's sniffing, the learner explodes, because now it can't find a very good pattern. Not a huge, not a very powerful example, but powerful enough to keep us interested. The Lang-Wehagen algorithm is very simple to code, runs very fast, and like I said, it's very straightforward to plug in. The next thing that we went to, and I'm trying to go quickly because I know time is a factor, is fuzzing. So we have a bit of a hypothesis. I said we want to link it to the code where fuzzing is actually grammatical inference. And Michael Zalewski's AFL fuzzer, which I don't know if you've ever played with, great piece of code, just a blast just to turn on. That's the best. I love code you can just turn on. You don't have to do anything. So you can just turn it on and it starts organizing, going through test cases. And the nice part about it is it grabs these test cases and starts mashing them into little folders where it thinks they're interesting and building new test cases. And so it's this tree where it's kind of inferring what the code is doing, trying to get maximum coverage. But at the same time, he's got a blog post that actually spurred me to think he was inferring the JPEG standard. So he started out with a JPEG file that was just hello world in text. And he fed it to his fuzzer. And the fuzzer starts tweaking and tweaking and tweaking and tweaking and moving down the tree and trying to cover the code, and eventually comes up with a JPEG by mistake almost. So it's learning a grammar. Slowly, it's learning a grammar. It's not going to learn all of the test cases, but it's exactly what we want to do. And again, this is JPEG because I can't show you any of the other stuff we're doing, not because it's super secret or important, but because Form 1 release would have taken 7 months to get some of the stuff through it. So we did the JPEG thing, and you can see where the little bit tweaks end up with different pieces of code, but they're all parts of the grammar. So in most of our cases, we have a giant web server that'll do all sorts of different interesting things if you want it to, but we don't want it to do that. We want it to do like one thing, one endpoint. We want to make sure that works right. So with that in mind, the future work, where we're going now is basically exploiting all of this wonderful work for these folks that are doing binary analysis, static analysis, pulling, especially lifting code up into kind of a generic language so that we can either infer interesting grammars about that code, or we can feed data in and determine what branches of that code we think are safe. Now remember, we're not trying to solve all the problems here. We just have, to explain how the DoD and the military tends to work, first what you do is you decide you can do it better than everybody. Then you throw a bunch of money at it. And then you wait 2 years, and you come back and you realize, no, we can't do it better than everybody. We got to go buy something. And then you take 40% of the money you spent the first time, and you go pay somebody else to do it who also screws it up. And by the end, you end up with a little bit of money to try and do what you tried to do at the beginning, and then you start all over. So it's like a 5-year process. So when you talk about, it was interesting to hear this morning, maybe we could just deploy new code faster than they can find vulnerabilities. I'm working on a Linux box that I'm guessing hasn't had a piece of code deployed on it since about 2008. That's working for the military. It's just the way it is. You just can't do anything about it. So we have to take these old, broken, potentially terrible pieces of code and harden them up a little bit. And so the low-hanging fruit thing, that's our MO right now. Just harden what you can harden, and this grammar inference stuff seems to be working relatively well in terms of, hey, this is what we should be accepting. And there's some interesting results as well that are pretty preliminary, so I won't get into them here. But the simple stuff is definitely a good place to start. We've seen some ways to either normalize or to throw out, classify traffic very quickly. And the bottom one, of course, EFS seems intuitive. I don't know that it's all that intuitive. I need more Prolog programmers. So if you could spread the word, that would be outstanding. In the grand scheme of things, like I said, I think it's nice because it maps to the Chomsky hierarchy accidentally. You could give somebody a recipe and say, do this, don't do that. And you can at least restrict what they can do in terms of parsers. So with that, I'll end. I know that was a whirlwind tour and I didn't get into too much detail, but trust me, the detail gets ugly quickly.
All right, let's thank our speaker. We're kind of pressed for time, but I can take like one question. Yes.
Hey, great talk. I wonder if you studied dynamic synthesis of invariants for programs. There is like a field of research that's very interesting because a lot of these invariants are hard to synthesize. Mm-hmm. But if you could somehow find heuristics to do that, or I don't know.
No, it's a good point. And like I said, from our perspective, you have to remember that it's not like we are, we again being ARL, a single product organization, right? So we need something that is applicable to a heterogeneous, and when I say heterogeneous, everything from software-defined radios to web requests. And we're choosing ones that are kind of simple right now. So it's something we're definitely interested in. It's mostly time. Like we need to show quick wins to keep some money flowing because otherwise they will redirect. The 5-year cycle, we'll be starting it all over again. So yeah, thanks for we'd like to, it's just a matter of time. So, and on that note, if anybody's interested and wants to work with ARL, they are dying to get people to work with them. I was specifically told to come recruit people. So as a contractor, I don't know how that works, but let me know.
All right, let's thank our speaker again.